In the last presentations, we introduced systems engineering and described one of its key tenets, and we noted that you'd have seen when doing that system engineering has a number of advantages. So in this presentation, we looked then at the relevance and benefits of the system engineering discipline. System engineering principles and processes are applicable, although to varying degrees, to a wide range of projects. For example, NCIA 632 states that the standard itself is applicable to the engineering or the re-engineering of commercial or non-commercial systems or part thereof, any system, small, large, simple, complex, software intensive, precedented, unprecedented, systems that comprise hardware, software, firmware, personnel, facilities and so on, new systems and legacy systems. It's actually quite difficult to imagine a system that doesn't fit in that sort of description, so in other words, system engineering applies to all systems. However, while systems engineering may be applicable to all systems, we have to be very careful about how it's applied. Surely we can't do exactly the same things in large, complicated projects as we would in very simple, small projects, or else we'd take way too long and spend far too much, as well as take many unnecessary risks, by doing things that just simply aren't necessary. So clearly, different levels of system engineering are applied to each of these types of project, and the issues and the activities that we consider must be tailored for each individual project. It's critical, therefore, that we understand the merits of system engineering and apply them in a tailored manner, cognizant of the relative size, complexity and risks associated with each system development. And we'll return later and talk more about tailoring in systems engineering. Now, first we should observe that system engineering is relevant to all parties as well as to all systems, and it's particularly relevant to both the customer and the supplier. The customers use system engineering to define business, stakeholder and system requirements, as well as to monitor the contractor's progress and risk. The contractors use system engineering to develop effective processes for the design, development and the test of systems. So both parties are looking to produce quality systems while minimising their exposure to risk, and this is what system engineering can help them with. To be specific then, there are a number of benefits that come from applying correct system engineering processes. Firstly, there's a savings in lifecycle costs, and we saw those earlier. There's a reduction in the overall schedule. There's a reduction in risk, and it produces a higher quality system. Let's look at each of those in more detail. The first and most obvious benefit is the scope for saving money during all phases of the system lifecycle. We call those lifecycle cost savings. While some may argue that the additional resources and requirements imposed by system engineering can increase the costs, these increases are comparatively small and are generally felt in the very early design phases. If applied appropriately, system engineering can ensure that the savings achieved far outweigh the cost of implementing any small number of additional procedures and methodologies. Experience indicates that an early emphasis on systems engineering can result in significant cost savings later in the construction and production phases, in operational use and system support, and even in the disposal of the system. Now the figure here provides a simplistic illustration of the impact of systems engineering on the system lifecycle. This curve shows that system engineering has its greatest impact through the rigorous applications of processes and methodologies during the early stages of the project, where it's easy to change and it's cheap to modify. In fact, the curve in the figure has been labelled as the ease with which changes can be made throughout the system lifecycle. Now in the second curve in the figure, the greatest impact of requirements engineering can be seen to come at a time when the cost of implementing changes is lowest. That is, the earlier we detect and correct errors, the easier they are to correct. Consequently, system engineering provides the ideal opportunity to have the greatest impact on a project at a time when the changes are easiest and least expensive to make. It makes sense, therefore, that system engineering leads to a reduction in the technical risks associated with the system. Risks are identified early and monitored throughout the life cycle. Even early on in the process, a focused on feasibility analysis reduces the risk to the project. Through systems engineering, design decisions can be traced back to the original user requirements, and conflicting user requirements can be identified and clarified early, significantly reducing the risk of failure later in the project. Technical risk is monitored and assessed continuously through technical performance measures and design and reviews and audits throughout the system development. Finally, and probably most importantly, the disciplined approach to system engineering leads to a product that meets the original intended purpose more completely. Here we use the word quality to refer to fitness to purpose, or to the ability of the system to serve its intended purpose or its intended mission. In other words, this improved performance leads to a quality system where quality is measured by the ability of the system to meet the documented needs and requirements. If you're interested in reading further into the topics we covered in this presentation, you may wish to read the corresponding chapters in the texts associated with the course.